So in elastic collisions, both momentum and energy are conserved. And so this is different from, for example, inelastic collisions, where the two objects will stick together. In that situation, only momentum is conserved, energy is not conserved. Okay, so let's look at elastic collisions and see how that works. So we left this till the last because we were looking at collisions earlier and we hadn't treated anything with energy yet. So I decided to come back to this after we looked at energy so that we can treat this properly. So let's look at elastic collisions. So we consider two masses, M1 and M2, as shown below. Okay, so we have the two masses, M1 and the second mass, M2, and we have M1 moving this way and colliding with the second mass, M2. And we can keep M2 at rest if we want. So this is V1 initial, V2 initial equal to 0. So this is before collision. And then after collision, we have M1 this way, moving with velocity V1 final, and M2 moving with velocity V2 final. So we can now write the total momentum before the collision and total momentum after collision, and then we shall do the same for energy. So we shall say our approach is to write the momentum conservation principle. So we then use the energy conservation principle. So we're using both momentum conservation and energy conservation. Okay, so we use energy conservation before and after, momentum conservation before and after. So before, the momentum of object 1 is M1 V1 initial plus momentum of object 2 M2 V2 initial, which is 0. And then after the collision, momentum is M1 V1 final plus M2 V2 final. And by momentum conservation principle, by momentum conservation, M1 V1 initial is equal to M1 V1 final plus M2 V2 final. And then before the interaction, we have half M1 V1 initial squared, and then half M2 V2 initial squared, which is 0, since V2 is equal to 0, or since V2 initial is equal to 0. And then after the collision, we have half M1 V1 final squared plus half M2 V2 final squared. And then energy conservation means that we have the initial energy half M1 V1 initial squared equals half M2 V2 final squared plus half M1 V1 final squared, like that. So now we have two formulas to work with. So putting it together, we're going to have M1 V1 initial equals M1 V1 final plus M2 V2 final, and then we have half M1 V1 initial squared equals half M1 V1 final squared plus half M2 V2 final squared. Okay, so we have two equations now with unknowns in there that we can solve for. Our goal is to find V1 final and V2 final. Okay, we know the initial already, so we want to solve this for V1 final and V2 final. So this requires a little bit of algebra, but you can certainly do this. So I'm going to leave the algebra to you guys to do. You can see this done in a lot of the physics textbooks that are out there, so I'm not going to go through it. It's actually a long algebraic process, so you can find the answer and figure out how to do it, or go through the steps and learn how to do it. But I'll quote the final results. So final result V1 final is given by m1 minus m2 divided by m1 plus m2 multiplied by v1 initial, and v2 final is equal to 2 m1 divided by m1 plus m2 times v1 initial. So I wanted to write this final results down so we can go through and analyze it a little bit. So let's look at a few special cases. One of the cases can be m1 equals m2. So if m1 is equal to m2, then v1 final becomes equal to 0, and v2 final becomes equal to v1 initial. Okay, just by plugging in m1 and m2 into those two formulas, you will see that if the masses are equal, then all the energy of object 1 is transferred to object 2 when they collide. So object 1 comes to a stop and object 2 travels with the same speed as object 1. So the scenario is this. You have object 1, v1 initial, object 2, and then after the collision, we have v1 final equals 0, and v2 final equals v1 initial. So the object, this one is now at rest, and this one is moving with the velocity of the first one. So that's what happens after the collision. The second case, case 2, we can say that m1 is much larger than m2. So we have our formula v1 final equals m1 minus m2 over m1 plus m2 v1 initial, like that. Okay, so if m1 is much larger than m2, we shall have v1 final equals m1 over m1 v1 initial, which gives us v1 final equals v1 initial. Okay, so this will be the case where m1 is much larger than m2, and then v2 final, we have 2 m1 over m1 plus m2 v1 initial again. So we shall have v2 final equals 2 v1 initial. So in all these formulas with m1 much larger than m2, you can just ignore m2. And then case 3, m1 much smaller than m2, so v1 final is equal to m1 minus m2 over m1 plus m2 v1 initial. So the opposite case applies, and then v2 final equals 2 m1 over m1 plus m2 v1 initial. m1 much larger than much smaller than m2, and so you can think of it as 1 over m2. If m2 approaches infinity, then this is equal to 0. Let's look at perfectly inelastic collision also. So the difference between elastic and inelastic is that in the inelastic case, energy is not conserved. So consider a mass m1 moving with velocity v1 and colliding with a mass m2 at rest. After collision, the two masses stick together and move off with velocity v final. So we can draw this example again. This is m1, this is m2, v2 initial equals 0, v1 initial is velocity moving. So this is before interaction, and then after the interaction, the two stick together and they move off with velocity v final. So we can do momentum conservation. Momentum conservation gives m1 v1 initial plus m2 v2 initial should be equal to m1 plus m2 v final, not v2 but v final. And so we can see that m1 v1 initial is equal to m1 plus M2 V final, where V final then becomes M1 V1 initial divided by M1 plus M2. And then we will see that by energy conservation, we have half M1 V1 initial squared equals half M1 plus M2 V final squared. So what we can do is we can see what happens here. We know a formula for V final. We can plug it in there to see what happens, or we can put some numbers in. So we try an example. So you have all the necessary formulas, so you've done this before. So we have the mass that is moving, colliding with another mass at rest, and we want to see what the final speed is and if energy is conserved. So work on that and let me know what you find. So let me add to this question. When I say is energy conserved, I'm asking you to find the initial and final energies and tell me what you get, okay? So what is V final for the two masses stuck together? Or V, what is a V? You got 11 meters per second. Is anyone getting a different answer? So we have 11. Okay. So we have 0.9. 0.91 meters per second. You have 1.3.
1.3 as well as 0.
Say that again. I didn't understand.
Yeah, 1.34.
1.34. Okay.
We can have both answer, but we don't know why both answer.
You did what?
0.9 also. You can have 1.3 for us, but
as a solution.
Yeah.
Oh, I see what you guys are doing. Okay.
One is from momentum conservation and another is from.
Well, in this case, energy. Well, okay, maybe the way I wrote the question is not good. This is a very simple question actually. So we have M1 V1 initial equals M1 plus M2 V, right? Yeah. So V is just equal to M1 V1 initial divided by M1 plus M2. That's all you have to do to find V.
0.91.
Okay, so 0.91 meters per second. That's your V. So when I say it's energy conserved, what I want you to do is to find kinetic energy total initially, which is just half M1 V1 initial squared, like that. And then the final is just half M1 plus M2 V squared. So that V that you find here, you just put that here for the final to get a final energy. Okay, yes.
Why we cannot do like kinetic energy for the initial equals to kinetic energy to the final energy?
Well, that is the whole point, that energy is not conserved.
It should say like elastic collision or
This is inelastic. This is perfectly inelastic. You see the two are stuck together. It's not an elastic collision. Energy is only conserved in elastic collision. In all other collisions, energy is not conserved. So momentum,
right?
what is that?
Right there. It is like inelastic collision.
Yeah, this is inelastic. So if you look at, this is what I said. So it says here, let's look at perfectly inelastic collision. So if in all collisions, momentum is conserved. Energy is only conserved in one collision, perfectly elastic collision. In the other ones, energy is not conserved. So we can't set it equal. Okay, so that's why I wanted you to calculate the energy before and calculate the energy after. So what is the kinetic energy total initially? That we have times M1, which is 5 grams, is 0.005 kilograms, right? So 5 grams is 0.005 kilograms times V initial. What was V initial? 2 squared. So what does that give us? 0.01 joules. And then what is final kinetic energy? And you said this was 0.91 squared. So what does that give you?
0.045. 0.0045.
Okay, so the whole point of this exercise is that energy is not conserved. You see, we've lost a lot of energy. You see, so we can't set them equal. If you set them equal, then you get a wrong result. So the energy lost is the ratio of the sum of the two masses, really. So it's really cuts the energy in about half, because the two masses are m1 plus m2. So we can look at how this works.
And you just mean you converted the grams into kilograms.
Yes, I did. So let's look at the theory of why this works that way. So we said that by momentum conservation, V was equal to m1 v1 initial divided by m1 plus m2. And then by energy conservation, we had half m1 v1 initial squared equals half m1 plus m2 v squared. So all you have to do now is to take your v and put it here. You see that? So you're going to have half m1 v1 initial squared equals half, and then you have m1 plus m2, and then you take your v and put it there. It becomes m1 v1 initial divided by m1 plus m2. You are squaring this. Okay, so this is what you have. You can see now that the two are not equal. Do you see that? So these are not equal, so energy is not conserved. You can go through the algebra and divide things out and get an answer. But if you just put in the masses, you will see that we get the result that we saw, that the final energy is going to be about half of the initial. Any questions at this point?
Since they are not equal, which one is not equal?
The one on the left is larger than the one on the right, because the one on the right is dividing several masses, m1 plus m2. So let's do an approximation. Okay, do you see how that is looking? You see that? So you will see that the result we got, if you look at the result we got earlier, 0.01 and 0.0045. 0.0045 is about half of 0.01. You see that? But the reason why it's not exactly half is because you see the masses are not exactly equal. This is 0.005, 0.006. That's why we got 0.045. It's a little bit less. But if the masses are exactly equal, then this results 0.01. This is 0.01. This is going to be 0.005. It's going to be exactly half. You see, like what I got here. You see that? So that means that these two are not equal, as you can see. See, this is going to be, so it's going to be half m v1 initial squared equals 0.5 of half m v1 initial squared. So the final is about half of the initial when they stick together. Any questions?